Hi everyone, welcome to the after credits scene. This video is completely optional. Nothing on this is going to be on the test. I'm going to talk about all of the things that we initially planned to do, which then reality took place and we never got to do. Also, this video is completely unscripted, so I'm just winging it. You can see whether it goes better or worse than the ones which I was reading off a script. Okay, so there are basically three topics that we planned to do that never happened, which kind of all came together into a grand finale. The first one was something called modal logic, which is a way of adding unary proposition constructors in order to reinterpret propositions as being conditionally true depending on something in the external world. And I'll explain something about what this means. Then we have a trick for turning regular expressions into a programming language. And then we put these two things together in something called dynamic logic, which gives us a logic for reasoning about programs. And so the programming language that we get from regex is a ordinary imperative programming language with variable assignment and loops and this kind of thing. So not a functional language or any of the other weird things, but a kind of normal imperative programming language. And then dynamic logic gives us a way of reasoning about what imperative programs do. So the original intended end goal of this course was to be able to write proofs about what imperative programs with things like loops will do. And we plan to culminate in a correctness proof for some kind of sorting algorithm with variable using loops and variable mutation. Okay, so so modal logic is a way of it's a form of propositional logic. So the type that we were doing back in weeks 1 and 2. So no variables initially, no equations. Sorry, but then you add one or more unary constructors for your proposition. So not as an example of a unary proposition constructor. So this arose out of philosophical logic, and the original example was necessary. So we write. So this is the traditional notation is a little square symbol. This is the closest I can do on a keyboard. So this is box P. So box P means that the proposition P is necessarily true. And this was an old. I mean, this is philosophy, but this was an old problem in philosophy. Is what does it mean? What's the difference between something that's true and something that's necessarily true? So for example, 2 + 2 = 4 is necessarily true, but there are 8 planets in the solar system. It's true, but not necessarily true, because when I grew up, it was a different number. And so it turns out that this thing has very neat rules, because you have an elimination rule that says that if something is necessarily true, then it's true. And you have an introduction rule that says that if something is necessarily true, then it's necessarily true. So these are the two basic rules. And then we also have a kind of a mapping rule that says that if P then Q and necessarily P, then necessarily Q. So these are the basic laws governing the necessary connective. And then we get another one, which is not necessarily not P. And you have to think a bit and tie your brain in a knot to decide how do you interpret not necessarily not P? And the answer is possibly P. So this means that P could be true. And then we write this then as diamond P, and then this satisfies some exactly dual rules that says that if P is true, then P could be true, And if it could be true that P could be true, then P could be true. Okay. So philosophers invented this thing, and then computer scientists seize on it as something that's extremely useful for all kinds of things for talking about. So philosophers were talking about the quote unquote world, whatever that is, but we want to talk about things we can actually get our hands on, like computer systems. One flavor of this, so there are many flavors of modal logic, depending on how you interpret these things and exactly what rules you make provable. You can customize it a lot. So a common one is called temporal modal logic, and there we have connectives like this means that, so future P means that P will be true at some point in the future. And then GP, this is globally P, means that P is true at all points in time. So a typical formula that you want to prove about a system is that at all points in time, if you have a request, then at some point in the future, it will be answered. So this is a typical liveness property for a server. So when we do systems verification, we're often formally proving formulas like this. Okay. That's enough on the first topic. I'm going to come back to that in a minute. So now we need to make regexes into a programming language, and the way that we do this is by picking the alphabet very carefully. So we just do ordinary regexes, but over a particular alphabet. And I'm going to say a command, and I'm going to parameterize this by a set of variables, which is a trick that we saw back in week 4, probably. So these are going to be atomic commands. So I'm not calling them int now, am I? I'm calling them natural numbers. So this thing means assign a natural number to a variable. So these V is going to be my type of assignable variables. So this is the most basic atomic thing that you can do in an imperative programming language, is assign a value to a variable. And the other thing that we need is a conditional test. I think I want to make this these can be expressions, so I want these to be expressions that can involve variables in V plus some arithmetic operations like plus and times and whatever. And then also I want to be able to test, and then this. So the idea of this thing is that this atomic regular expression is going to behave like the regex I when this Boolean is true. And I want this also I'm going to make this expressions as well. These are now Boolean expressions, because I want these to also be able to involve my mutable variables. This thing, when the condition is true, is going to behave like the regular expression I, which does nothing, but when it's false, it's going to behave like the regular expression Z, which fails. So so the idea is, so now we're going to form regular expressions over my variables. Just give me some actual variables. And now the idea is that, so regular expressions give us all the constructors that we need to make a programming language. So for example, we have, I can say like assign a 1, and then so I'm going to use the times constructor for regular expressions, then assign b 2. So this looks like the program a equals 1, b equals 2. So star is going to behave like semicolon in C style languages like JavaScript, so sequencing. And then star is our looping construction. So so I'm pretending that this is now an expression. This thing says increment a forever. Okay. So this is going to be a loop that never terminates, but I can make it terminate by using putting a test on the front. So I'm going to say, this thing, what am I saying? These things should be atoms, right? We can lift atomic regular expressions using the atom constructor of the reg type. This is just the same regular expressions we've been using the whole time. So to guard this loop, to stop it from running forever, I can precede this with a test like, so this now says something like, while a is less than 10, increment a. The syntax, as with everything in this course, the syntax is completely horrible, but semantically, this language allows us to write kind of imperative programs. We can also like we can add whatever else we like here. Like we can give it some IO capabilities if we want. So the idea is that this star will try to loop forever, but at some point when this becomes false, then this will behave like Z, and then that kind of prevents the star from looping anymore. Okay. So now we put these previous two topics together. So now we're going to make a modal logic where we get one modality, one unary connector for every regular expression. So we can write something like this, and this says that after executing the regex R, P is true. So now we want to do this for our particular regexes over our particular command language. So then we want to say something like, after running sine v e, then the proposition v equals e becomes true. I'm starting to abuse notation more and more because this thing isn't technically equals, but it's some kind of prop on variables and expressions. But this is the kind of basic fact about variable assignment, is that immediately after making a variable assignment, it becomes true that the variable equals the thing that you just assigned to it. And then we have a bunch of laws about this, like if P is true, then after doing the regex I, P is true. And if after doing R1, then after doing R2, P is true, then after doing R1 times R2, because it sequences these two things together, P is true. So this is our introduction and elimination rules. And then we're going to get a much more complicated rule for loops, and I probably am not going to be able to figure out the rule from loops from memory. But the rule for loops is going to say something like, in order to prove that something is true after the loop, we need to pick a formula and prove that that formula holds at all points when the loop is running. So this is called a loop invariant. So essentially we do a proof by induction on the loop. So we have to prove that the invariant is true initially before the loop runs. And we have to prove that if the invariant is true after some number of iterations of the loop, then it remains true after one more iteration of the loop. And then this allows us to conclude that after the loop terminates, then the invariant is true. And this is essentially the only rule that you need to reason about loops. It's very powerful. So we can use that to write correctness proofs for all kinds of interesting imperative programs. Is there anything else I want to say about this? Oh yeah, the basic the classic form of condition you want to write is a precondition postcondition relation about a program. So you want to say something like so P is now a precondition. I want to say if the precondition is true, then after running a program, I want to call this A instead, then if the precondition is true, then after running the program, the postcondition is true. So this allows us to completely write the specification of a program. So it's a thing that turns preconditions into postconditions. And then these things can be sequenced together, because then if we have another program whose precondition matches the postcondition of this one, then between these two things, we're allowed to conclude that if P is true, then after running A, then B, then R is true. So this is the kind of the reason that we do logic in computer science can be traced all the way back to sometime in the 60s, when people worked out that you can reason about programs in this kind of way, by triples consisting of a program, a precondition, and a postcondition. Okay, I think that's all I want to say. So yeah, we planned kind of this grand finale where several different threads of the course were going to come together and unify into one thing. So regular expressions were going to be unified with logic and with programming, and everything was going to be great. And then things unraveled, and none of that happened. But this gives you a kind of idea what we were planning.